How did the universe begin? And what were its early days like?
The most widely accepted explanation for the origin of our universe is the Big Bang Theory. This theory suggests that our universe began with a massive, unprecedented explosion that set galaxies in motion, hurtling them away from each other at incredible speeds. The observation that galaxies are rapidly moving away from us in all directions, as if propelled by a powerful force, led to the development of this theory.
In the 1920s, Belgian priest Georges Lemaitre proposed the Big Bang Theory, suggesting that the universe originated from a single, ancient atom. Later, Edwin Hubble's observations of galaxies moving away from us in all directions provided significant support for this idea. Additionally, the discovery of cosmic microwave radiation by Arno Penzias and Robert Wilson in the 1960s was seen as a key confirmation of the Big Bang Theory, with this radiation being viewed as a lingering echo from the universe's beginnings. Further work has helped clarify the Big Bang's tempo. Here's the theory: in the first 10 to the power minus 43 seconds of its existence, the universe was very compact, less than a million billion billionth the size of a single atom. It's thought that, at such an incomprehensibly dense, energetic state, the four fundamental forces, gravity, electromagnetism, and the strong and weak nuclear forces were forged into a single force, but our current theories haven't yet figured out how a single, unified force would work. To pull this off, we'd need to know how gravity works on the subatomic scale, but we currently don't. In the universe's earliest moments, particles were packed incredibly tightly, allowing them to interact and reach a uniform temperature. Then, in a fleeting instant, the universe expanded rapidly and evenly, with tiny quantum fluctuations introducing slight variations. This inflationary model offers an explanation for the universe's remarkably consistent temperature and matter distribution, suggesting that the universe's initial expansion was incredibly rapid and uniform. After inflation, the universe continued to expand but at a much slower rate. It's still unclear what exactly powered inflation. As time passed and matter cooled, more diverse kinds of particles began to form, and they eventually condensed into the stars and galaxies of our present universe. By the time the universe was a billionth of a second old, the universe had cooled down enough for the four fundamental forces to separate from one another. The universe's fundamental particles also formed. It was still so hot, though, that these particles hadn't yet assembled into many of the subatomic particles we have today, such as the proton. As the universe kept expanding, this piping hot primordial soup, called the quark-gluon plasma, continued to cool. Some particle colliders, such as CERN's Large Hadron Collider, are powerful enough to recreate the quark-gluon plasma. Radiation was incredibly intense, allowing photons to collide and create pairs of matter and antimatter particles. These antimatter particles were identical to regular matter particles but with opposite electrical charges. It's believed that the universe initially contained equal amounts of matter and antimatter. However, as the universe expanded and cooled, the photons lost energy and could no longer create matter-antimatter pairs. This led to a cosmic game of annihilation, where matter and antimatter particles paired up and destroyed each other, leaving a surplus of regular matter in the universe. Somehow, some excess matter survived, and it's now the stuff that people, planets, and galaxies are made of. Our existence is a clear sign that the laws of nature treat matter and antimatter slightly differently. Researchers have experimentally observed this rule imbalance, called CP violation, in action. Physicists are still trying to figure out exactly how matter won out in the early universe. A tiny, ghostly particle called a neutrino and its antimatter counterpart, an antineutrino, could shed some light on the matter, and two big experiments, called Dune and Hypercameo-Candy, are using these chargeless, nearly massless particles to try to solve the mystery. There wasn't a single star in the universe until about 180 million years after the Big Bang. It took that long for gravity to gather clouds of hydrogen and forge them into stars. Many physicists think that vast clouds of dark matter, a still unknown material that outweighs visible matter by more than 5 to 1, provided a gravitational scaffold for the first galaxies and stars. When the first stars lit up, their radiant energy ionized neutral atoms, marking a pivotal era in the universe's history called reionization. Scientists have attempted to witness this cosmic dawn, but the findings have been inconsistent. In 2018, an Australian team claimed to have detected evidence of the first star formation around 180 million years post-Big Bang, although their results haven't been replicated by others. By 300 million years after the Big Bang, the first galaxies emerged, and over billions of years, stars, galaxies, and galaxy clusters have continuously formed and evolved, ultimately giving rise to our own Milky Way galaxy and solar system. Even now the universe is expanding. To astronomers' surprise, the pace of expansion is accelerating. Estimates of the expansion rate vary, but data from the James Webb Space Telescope adds to a growing body of evidence that it's significantly faster than it should be. It's thought that this acceleration is driven by a force that repels gravity called dark energy. We still don't know what dark energy is, but it's thought that it makes up 68% of the universe's total matter and energy. Dark matter makes up another 27%. In essence, all the matter you've ever seen, from your first love to the stars overhead, makes up less than 5% of the universe.